instead of drawing a scale diagram, we can rather resolve the vectors into their components. So here we have the 3 vectors. So what we're going to do is we're going to resolve each of these 3 vectors into their horizontal and vertical components and then add those, and we know that the sum must be 0. How do we know? Because we know that the situation is in equilibrium. There's no acceleration of the stone, so it must be in equilibrium. So the resultant must be 0. And when the resultant is 0, the sum, this symbol means sum, the sum of the x components must be 0, and the sum of the y components must also be 0. And we can make use of that fact to solve this problem without having to draw a scale diagram. Remember, we have our Cartesian plane, and things that lie on one particular axis can be added algebraically, where we have positive and negative referring to direction. We're going to use to the right as positive, to the left as negative. We're going to use up positive, down negative. Here we have our 3 vectors in situ. There I've just rearranged them so that they make a closed vector diagram showing that there's 0 resultant. They are in equilibrium. But these 2 diagrams are equivalent because you are allowed to move vectors as long as you don't change their angle or magnitude. And now what I'm going to do is for each of the 3, here are the 3, I'm going to calculate the horizontal component and the vertical component, and we know that the sum of all the horizontal components must be 0, and the sum of all the vertical components must also be 0. And that fact is going to help us to find out the unknown values, namely what is T2, what is T1. So we start with the weight. The weight is really easy because the weight only has a vertical dimension, 800 newtons, and its direction is downward, which we choose to be represented by the sign negative. Negative 800 newtons. This is a Cartesian plane. Let's put our vectors on top of this Cartesian plane with the point of interest at the origin. So there we have it. Now let's focus only on T1 and let's get the horizontal and vertical components of T1. So there we have the whole situation on our Cartesian plane with T1 highlighted. T1 acts at 30 degrees to the horizontal. We draw a construction line such that we have a right angle triangle, and we know that T1's x component extends from the origin up to that construction line. How can we calculate the magnitude of T1's x component? Then we draw another construction line such that we have another right angle triangle around T1, and we use that to represent T1's vertical y component. You might want to pause the movie here to remind yourself of the trigonometric functions. Also remember that if we have the angle theta as being to the horizontal, as in this particular case, then we can find fx, the horizontal component, by multiplying f's value by cos theta. And we can find fy's value by multiplying f's value by sine theta. So to find the horizontal component of T1, we multiply T1's value by cos 30 degrees, because 30 degrees is the angle T1 makes to the horizontal. Now, we cannot substitute a value into T1 because we don't know, but at least we can just calculate what cos 30 is, 0,866. So we can give T1's x components value in terms of T1. We can't give the final answer yet, but we can give it in terms of T1. T1 multiplied by 0,866. And we know that the direction is to the right, which we have chosen to be positive. So therefore we can call it positive T1 0,866. T1's x component is positive T1 multiplied by 0,866. Now what about the vertical component of T1? We find that by multiplying T1 by sine of 30, because 30 is the angle to the horizontal. So in effect, we are moving T1y to make this triangle here, where we're going to use opposite over hypotenuse, sine 30. Because obviously, these two sides are equal to one another. On our calculator, we type 30 sine. We find the answer is a half. So this value here, we don't know T1, so we cannot substitute into T1. T1, but we can give it in terms of T1. T1 times a half. And we know that its direction is upward, and according to our Cartesian plane, upward is the positive direction, and so we give that as positive T1 0,5. Put that in our table. The vertical component of T1 has a magnitude T1 multiplied by 0,5 in a direction upward, positive. Now we focus on T2. T2 acts at 50 degrees to the horizontal, but now towards the left. We put in construction lines so that we have right angle triangle there, and use that to get the horizontal component of T2. Put in another construction line such that that is a right angle, and that gives us the vertical component of T2. Remember our trig functions, and remember these formulae for resolving a vector into its components as the angle is to the horizontal. So we start by finding the horizontal component of T2. That's equal to T2 multiplied by cos 50. Put cos 50 on your calculator. You find the answer is 0,643. We cannot multiply that by a value for T2 because we don't know what it is, but we give T2x in terms of T2. We know that this is to the left, and according to our Cartesian plane, to the left is negative, and so we have the magnitude of the x component of T2 as T2 multiplied by 0,643 and the direction as negative. We put this into our table. Now we need the vertical component of T2. So the vertical component there can be thought of as being moved so as to complete this triangle here so that it is opposite to the 50 degrees, so we can use sine 50 degrees to find it out. This side and this side are equal to one another. Sine 50 degrees is equal to 0,766. We cannot substitute a number into T2 because we don't know it, but at least we can give the vertical component of T2 in terms of T2. We know that the direction is upward, and from our Cartesian plane we know that that is positive, and so we replace that by a positive sign and we put this into our table. So now we have the horizontal and vertical components for each of the three vectors, and we know that they add up to 0 because this is an equilibrium situation. So what we need to do now is add these algebraically. We can add them algebraically because they all act on the same line. Well, all the x ones act on the same line as one another, so we can add them up algebraically and they must equal 0. And all the y's act on the same line as one another, so we can add them up with one another algebraically and they must equal 0. Because in equilibrium, remember, the resultant is 0. So the sum of the x components is 0, the sum of the y components is 0. So that's what we do here. Sum of the x components must be 0, the sum of the y components 0. So notice 0 equals, okay, I suppose I should have said 0 plus, but obviously I don't need to. That's that. 0 placed there. Plus this value here, T1's x component, plus this value here, T2's x component. And the sum of the y components must also equal 0. So 0 is equal to minus 800 plus T1's y component plus T2's y component. So let's start with the sum of the x components. So I've simply taken what I'd written in the table and written it out again. So if you need to see where I got this from, just go back one slide. 0 is equal to T1's x component plus T2's x component. Make sure that you do put the signs in correctly. Now notice you cannot go and just subtract. You cannot say on your calculator 0,866 minus 0,643y, because this is multiplied by T2 and this is multiplied by T1. So you can't add, or in this case subtract, apples and bananas. They're different things. So what progress can we make? Well, the first thing we can do is move one to the other side. How do we do that? Well, let's say we move this one to the other side. To do that, we subtract T1 times 0,86, and what we do to one side we must do to the other side, otherwise it's illegal. So what that does is it makes minus T1 times 0,866 is equal to plus T1 0,866 minus T1 0,866 makes 0. So that cancels away. So it's equal to minus T2 times 0,643. 0.6743. We can divide both sides by -1 to get rid of the minus signs. And then I can give T1 in terms of T2, or the other way around. T1 is equal to, I can divide both sides by 0,866. 0,866, which gets rid of this 0,866. What I do to one side, I must do to the other. I divide it also by 0,866. That gives me T2 times 0,643 divided by 0,866. And you can then do that on your calculator. And when you do, you will see that the answer is 0,7425 and some other decimal places. You shouldn't clear your calculator. Keep all of those decimal places, put it in the memory, because the more decimal places you have, the more accurate. So you see, we haven't found T1, nor have we found T2. But what we've done here is we found how to express T1 in terms of T2. So if we would know either of them, we could then solve the other. And that's what we're going to do next. So now let's turn to the y component sum, which is again equals 0. So I'm just going to take this and write it out nicely. That's what I've done here. And let's see what can we do with this. At the moment it doesn't seem like much, but we remember back to what we've just done. And we have found that T1 is equal to T2 multiplied by 0,7425. So we can substitute that value where we see T1. So instead of that T1, we can rather put in that value there. And in that way, we get rid of T1 and we only have T2s. Then we only have one unknown and we can solve for that unknown. So that's what we're going to do. So notice, I've just spread the first line out here. It's exactly as I had before. And now what I've done is, instead of writing T1, I've written this value, which is the same thing as T1. And there it is, still multiplied by 0,5. So now these two can be added together because they are apples and apples. They are both T2s. So the first thing we can do is to take this minus 800 newtons to the other side of the equal sign. In other words, add 800 newtons to both sides. What you do to one side, you have to do to the other. So that makes it 800, positive 800, is equal to, and then these two cancel out, so it's 0, but of course we don't need to write it, plus these values. So that's where we are over here. Let's look at this. So there we've moved the 800 across there, as I've just said. Now this T2 multiplied by 0,7425 halved gives you T2 0,371. Check on your calculator. If you take this value and multiply it by a half, by 0,5, it gives you 0,371. And since that's a T2 and so is this one, you see I've just carried this T2 down. They are both T2s, you can add them. So 0,371 plus 0,766 gives you 1,137. Of course, don't forget the T2s. So then you can divide both sides by 1,137, which gives you T2 alone on one side. I've just swapped the sides. I've made it now to be on that side, but it really doesn't matter. And 800 divided by 1,137 on the other side. So we have T2 is equal to 800 divided by 1,137. Do that on your calculator. You find the answer. Of course, it's newtons. T2 is 703,45 newtons. And then we can use that fact to find what T1 is, because we can substitute 703,45 into T2 and from that find T1. So let's do that. We've previously seen that T1 is equal to T2 times 0,7425. Look back if you can't remember where we saw that. All we do is substitute this value into there, multiply 703,45 by 0,7425. Do that on your calculator and you should find 522,3. Of course, that's newtons. So if we go back, what was our question? What's the magnitude of tension 1 and the magnitude of tension 2? We have found tension 1, 522,3 newtons. By scale construction, we got 520 newtons. You can't be as accurate by scale as you can by calculation. And T2's value, 703,5, newtons. By scale, we got 700 newtons. Again, you can't be as accurate by scale as you can by calculation. Now, it might seem like the calculation I've just done is a lot longer than the scale, but as you get good at it, you will find that it is quicker, more accurate and easier, but only of course if you practice. Let's just remind ourselves, what have we actually done? We took the diagram, we deduced the angles shown here, and then we resolved each of the three components from that diagram into the x and y components. We added all the x components algebraically, and we know that the answer must be 0 because the situation is in equilibrium. We added all the y components algebraically, and we know that the answer must be 0 because this is in equilibrium. So that's what we were doing here. We got the sum of the x components to be equal to 0, the sum of the y components to be 0, and then the rest was algebra, which obviously needs a lot of practice that you don't make mistakes. But with practice, you can solve this problem using the resolution of vectors into their components rather than needing to draw a scale diagram.
And before we go, have you already liked? Have you subscribed? Have you left me a comment? And please go and visit my website. You'll find a lot of resources there, and they're categorized in a way that will make it very easy for you to find what you need. Until we meet again, learn science!